Hey everybody, welcome to Open Space for Monday, January 18th, 2021. So again, we are continuing to experiment with the new format. I hope those of you who watch this live, you're not going to watch it again to see the version with all of the cool graphics and music and edits and stuff. So yeah. Anyway, so and for those of you who are watching it afterwards, then you're missing all the preamble and all the stuff that I guess Chad is going to be hacking out. So I guess it's almost like it's two different audiences at this point. But just to give you sort of an update on what we've done. So last week we recorded Open Space, and then after the show, I made the show hidden, and Chad edited together a version that looks just like the original Q and A's. So we numbered it number 131, and then this one is going to be number 132, and this is also going to go away, I think, depending on what Chad wants to keep around. But we're trying to make it so that the two merge together. So people who've asked questions in the past or in other venues like on Patreon or when we get our Discord server going. I just need to sit up more, Chad. When we get our Discord server going or updated and a bunch of other stuff, then I'll bring in those questions into this and we'll go from there. So I've got a couple of questions that are prepared, and I'm going to start with those, and then we will get on with the questions that you have live. And you can, of course, jump on from the questions that have already been asked here, or if you've just got whatever original questions, go ahead and hit me with them. So the first question comes from Leif Gunnarsson. And this was in relation to last week's episode, asking, how would these gram-sized star chips communicate back to the Earth? I imagine many megawatts of transmitter power would be required, not to mention the extremely large antennae on the transmitting end also needed once reaching the destination. So this is a question, this is related to this idea of the breakthrough starshot. And you're sending these spacecraft, they could be just really small, just the size of, a couple of grams, and they're going all the way to Alpha Centauri. And the question is, how will they be able to communicate back to Earth? Because when we think about things, you've got, say, New Horizons, it's got a fairly big transmitter, and it's communicating back to Earth, and it's only coming in at a few kilobytes per second. It's a difficult job to try to be able to gather up all that data. And I actually had a chance to ask this question to Professor Avi Loeb. And for those of you who don't know, Avi Loeb is one of the sort of brains behind the Breakthrough Starshot organization. He's one of the people who developed all the math for the Event Horizon Telescope. He's the one who's been doing a lot of work on trying to figure out what Oumuamua is. And he's sort of like, on the one hand, does some of the most complicated astrophysics, black hole research, Einsteinian calculations. And then on the other hand, you've got, he likes to dabble in more popular science ideas, like what is Oumuamua and how can we send spacecraft to other star systems? And in his opinion, you can still communicate with the Breakthrough Starshot probes even when they're a couple of light years away, all the way to Alpha Centauri. They'll be transmitting. As long as you have a big enough receiver here on Earth, you'll be able to receive the information. It's going to have to be a very big receiver, and you're not going to get a lot of data very quickly, but it will be possible for those spacecraft, as long as they aim their beam, as long as they aim their transmission directly back at the Earth, and you got a really big receiver that's being able to receive it. So I thought it would be impossible, or I have sort of imagined in my mind there would have to be some kind of chain of spacecraft that would be transmitting the data all the way back to Earth. But nope. the spacecraft would be able to make the transmission all the way back to Earth as long as they're using a tight beam and they're aiming straight at Earth, and we've got a really big receiver that's able to watch for them. All right. Kelana Nalur asked, I have this question that I've never been able to get an answer for. Oh, let me just scan here. Kelana Nalur. I have a question that I've never been able to get an answer to. If we develop near light speed travel today, could we immediately begin sending ships out at light speeds arbitrarily close to see what is the farthest into the observable universe that we could get? That's a great question. When you think about the observable universe, we're able to see all the way back to the moment pretty much just after the Big Bang, about 300,000 years after the Big Bang. But those places, although they were really tightly, in fact, they were probably within about 1 million light years of each other back at the beginning. And then through the expansion of the universe, all of that stuff is now 46 billion light years away, and getting farther and farther away from us faster and faster and faster. And the reality is actually about 94% of the observable universe that we can see today is going to fall over the cosmic horizon. Even if we could travel at the speed of light, we couldn't reach 94% of the universe if we left right now. And that only leaves us actually 6% of the observable universe that we can actually reach. Close-ish galaxies, galaxy clusters, things like that. But beyond a fairly small bubble of the universe, even if we left right now, traveled at the speed of light, we could never reach them. Oh, I messed that up. Okay. All right, so those were the preamble questions. Chad, I apologize. I didn't press the answer question button, so the timing's going to be off. Oh well, we'll get the hang of this. All right, let's get into the actual questions for today. So Arjone asks, did they ever tell us why the SLS test was so short? So if you watched with all of us on Saturday, the Space Launch System did the full integration test of the core stage and the 4 engines. And that's like, when you think about the Space Launch System, that's the middle part without the 2 boosters and without the upper stage, the core stage. The giant hydrogen, oxygen, fuel tank, and the 4 RS-25 engines. Those are the engines that came from the space shuttle. They're the most beautiful engines that have ever been made, and now they're going to be destroyed with every Space Launch System launch. Nonetheless, the goal was to run these engines, run all 4 for 8 minutes, doing a full test to demonstrate that they would all work separately, they would all work together as a unified thrust system to carry this rocket into space. And what we saw was they went for about a minute and then they cut off. And there was like a major component failure as part of the process that they decided to cut off the engines. We don't know why yet, but it is kind of embarrassing. I mean, obviously, like, it's rocket science, right? And rockets are incredibly difficult. But the problem is that this is a moment that NASA has been working up to for 8 years, close to a decade, for us to actually see this rocket be tested in full configuration, and it didn't work. So now engineers are going to have to go and take the thing apart and figure out what the problem is and try the new components and stack everything, organize everything again and run the full test again. We're looking at delays. No one has said that we're looking at humans on the moon by 2024 delays. No, that's still the plan, man. But you know how this is going to go, right? That we're going to see delays, and it's going to slip to 2025, and it's going to slip to 2026, and maybe it's going to slip to 2028. So we'll keep you posted as there are more, more examples. Devil Deerstalker Deer Hound is saying, embarrassing, this is why we test tough. This is absolutely, I mean, of course, we have to test, or NASA has to test all four engines working together. This has never been done before with the fuel tanks that are part of the Space Launch System. The problem is when you look at, say, Starship is an entirely new concept of a rocket, has the same kind of launch capability as the Space Launch System, maybe more, and it didn't exist on 2 years ago. So what it is more is that it's all in the timing that this has taken a long time to even get to this point. And it's, I mean, there are all kinds of political reasons why NASA is in this situation. And, that's probably the topic of another video. All right, let me pick another one. All right. Oh, and they disappear when I answer the question. Okay, that's a problem. Yeah, okay. Apologies. We've got a system that lets me see all the questions and behind the scenes, but we're still figuring it out. All right. Okay, we'll do this one here. So T Home asks, if we find aliens and their civilization is so far away that we can never physically meet them due to the expansion of the universe, what messages would you want to send them? So part of the problem with what I just mentioned is this idea that these, even if we went at the speed of light, we could never reach them. So so we can't even send them messages to these ones that are going to be over the observable universe. The only ones that we actually can send messages to are the ones who are outside or within this range, this reachable universe, this explorable universe. But maybe we just can't explore them anytime soon. If we knew there were aliens on some other planet out there in space, is it a good idea to send them a message? I don't know about that. I've mentioned in the past that life on Earth, life itself, has given away the fact that we are here for the last 500 million years. We've seen, that oxygen in the atmosphere has just given off this very clear signal that there is something going on planet Earth. And so pretty much any star system with a powerful enough telescope within 500 million light years of us would know that we're here. That said, if let's just say they're stupid and they didn't realize that we were here, but they do have powerful fleets of warships, do we tell them? I don't know. I don't have any problem with sending messages out into the universe, potentially reaching other alien civilizations, because I think they already know that we're here. But if they are dangerous and they don't know we're here, I think it's best to keep our mouth shut. Maybe. I don't know. I guess I know, like, a lot of people think, like, oh yeah, it's super dangerous. And that was like, if you've read the three body problem, this idea of the dark forest, the aliens keep their mouths shut and hope not to get noticed, because getting noticed is a bad thing. But do we send a message? I don't know. I mean, let's say that we could have had a friendly neighbor in Alpha Centauri, and we could communicate with them, and we would receive a round trip message every 4.5 years. So every 9 years, we would send a message to them, we get an answer back. And so you can imagine, after a while, if you were able to build up some level of trust with this other civilization, that you would start to share information. And it would be sort of on this delay. You'd be like, here's all the things that we know. And they'd say, here's all the things that we know. And then we'd be decoding each other's information. And I guess if, like, maybe we knew there was some civilization out there and life on Earth was almost doomed, and we thought we could just, like, give them one final download of all of our information, then that might be a thing that we would want to do. I don't know. I'm kind of torn, actually. Do we keep our mouths shut, or do we try to share and hopefully we can get, because if we did find, I know I'm rambling here, but if we did find an alien civilization that we could share information, it would be an incredibly useful swap of information for both civilizations, assuming we were roughly similar to each other. So there is tremendous value. And at the same time, like, they could send a virus, like some kind of computer virus that we would install in our computers. Now suddenly they take over our planet. So it's a tough one. I don't know. It's interesting. All right, let's do the next one. All right, Jay DeVoe says, who do you think will have the first station with a rotating habitat for humans? We need a method to produce centrifugal gravity to stay in place permanently. I've mentioned this many times that the biggest unknown that we have in space exploration is the reality that we don't have any kind of artificial gravity. Nobody has tested it in any significant amount in space. And so we know that in microgravity, there's something like 12 different effects on the human body, and 9 of them you can deal with through diet and exercise and medicine. But there's like a couple of them, your fluid redistribution, problems with your eyes, problems with your cardiovascular system, that just can't be solved. And so the only solution is that we have to spend time in gravity. And we know that we can produce artificial gravity through some kind of rotating space station that provides centripetal force, and it feels kind of like gravity, although it's very weird. Like, it's not exactly gravity. It's gravity on a roller coaster, gravity on a wow, what was that amusement park ride that goes around and around and around? Cyclotron, I forget what it's called anyway, and you sort of smashed against the side. And so if you were in some kind of fairly small artificial gravity, something was rotating, you would feel these really weird effects where your feet were moving at a different speed from your head. And the test that NASA and other space agencies has already done is that it is apparently very disorienting. So we don't actually need a gigantic kilometer-sized 2001 giant ring that's spinning in space. All we probably need is one that is small enough to provide some level of artificial gravity that can be endured. So, you're not trying to get the one that you can't notice it. You want the one, and in fact, they can be fairly small. Like, you could have one that is sort of like a tiny little centrifuge that's only say 5 meters across, something that would fit inside a SpaceX launch fairing. And it would be like counterweighted with like 2 little pods, and you would lie down inside of it. Oh, sorry about that. And you would lie down inside of it, and then it would spin around, and you would experience 1G in this very tight little circuit. And you would spend time, like a couple of hours, maybe every day, sitting inside this tiny little spinning centrifuge. And that would give you enough gravity. And you would want to vomit in the beginning. And so you would actually have to get practiced in sitting in this little centrifuge. And they would make this thing small enough and fast enough and provide enough gravity just to the point that a human being can handle it. You could also kind of imagine that you would have like 2, which are just the length of like a human body. You would just sort of stand in this little pod, and it would just spin around, and you would experience gravity for an hour, and then it would stop, and you would come out, and then that would be your exercise for the day. And there's been some tests here on Earth, and they've found that actually you can go very quickly, and the human body can become accustomed to this very uncomfortable feeling. And so the price you would pay is you would feel nauseous and dizzy, but what you would get the effect of gravity on your body. And it's not a very complicated thing, and it could be launched. There was an idea a couple of years ago to add a module to the International Space Station that would, it was called Nautilus X, and it would just be this little ring that would be bolted onto the side of the space station. It would spin, and the astronauts would lie inside of it, and it would provide them artificial gravity. So I'm amazed that we haven't just done tests. Like, again, we don't need this gigantic 300-meter ring, kilometer ring. We just need something small enough that can be endured to provide some level of artificial gravity. If we can crack this, then that is the one big missing piece of being able to fly in space. The fact that there are health issues that we cannot mitigate. The other one, of course, is radiation, but that you just block it. So, all right. So Kyle Hunt asks, can we identify which exoplanets we've discovered could see us through the transit method, meaning that they're lined up to see us transit our sun? Yeah, in theory, we can look out, once we've discovered planets, we can look out and we can find the ones that would know that we're lined up to them. But when you think about the geometry involved, right? So there's us, so there's the sun, and there's the Earth, and then there's the other star, and there's the planet passing in front of it. And so if we're aligned like this, and they're lined up for us, then we can see them transit. And if they're lined up like this, and we're lined up like that, then they can see us transiting. So we can tell which stars would be able to tell. If you think about it, there's like this band that extends out from the sun through the plane of the ecliptic out into space, and any planets, any star systems which are along that band would be able to see the Earth, even if they're tilted away from us. They would be able to see that we are that the Earth exists. And in fact, there's this really clever idea that had been proposed that you could, when you're going in front of like one of those stars, you fire a laser that off the Earth that perfectly compensates for the dimming in brightness that the Earth causes as it's passing in front of its star. And what you get is you sort of cloak the existence of the Earth to any planetary systems that are able to see us transiting, which is kind of a clever idea. We're just around the corner. Like when we get to 2026, when the extremely large telescope comes online, we'll have the ability to directly observe planets orbiting other stars. And this whole idea of needing to see the transits goes away. Also, Gaia is going to be providing incredibly detailed information on planets that are not perfectly lined up using astrometry, to essentially measuring the wiggles of the planets. As the planets are going around the star, they're going to be sort of wobbling in space. And you can tell that there's a planet there, and then you point the extremely large telescope at this wobbling star system, and you see the planet directly. At that point, there's no hiding. So it's sort of like a tiny little period of human history that the transit method was the way we found planets. It will end up being a 2-decade experiment, and then we're going to shift to some more productive planetary discovery methods. I'm going to press the button after the end of answering the question, Chad. This seems to work, and it refreshes the page. So, all right. So Joe asks, what do probes like Cassini use to change their orbit and move around? When spacecraft like Cassini and Galileo and the orbiters go to a star system, or even Juno, they have some propellant on board that will help them do essentially an orbital insertion into the orbit of the planet that they're looking to orbit. And NASA has got everything so perfectly calculated that then the spacecraft is doing these orbits around in the planetary system, while at the same time the planet and its moons are orbiting around. And the way things time, Cassini will make some close flyby into the Jovian or into the Saturn system and just do a close flyby of Rhea, and then come back out and then just do a close flyby of Titan, and so on and so forth. And sort of for the main mission, they've got all that fairly worked out, and they know all of the orbits that are going to be happening. They know every single orbit, and they know the movement of the moons, and they've got everything sort of perfectly tabled out. If a spacecraft does have some incredible new mission extension, it can have a little propellant on board. And so what they'll do is they'll get all of their main science goals fulfilled. And if they've still got propellant on board, then the scientists will work out new potential orbits. They'll go, well, if we used all of our remaining propellant, we could put ourselves into a new direction that would then allow us to have all of these encounters into the future. Or if we went into this direction, then we'd have those encounters. And then they've got to decide, do we want these ones or those ones? And they min-max and they do their math and they come up with a proposed series of close flybys that they can get the maximum amount out of their propellant on the spacecraft. It's amazing when you think about how the Earth is moving 30 kilometers per second around the sun. Saturn is moving, I don't know what Saturn's speed is. And they launched Cassini off of the Earth. It went into orbit, went on an interception course to Saturn, made a flyby of Jupiter, made a couple of course corrections, made its orbital insertion, and was exactly where it was supposed to be to carry out its entire mission, making various course corrections as needed as part of the plan. The distances are vast, and yet the engineers who are controlling these things can make them just perfectly line up. It's mind-bending. All right. Apologies. Lots of good questions. And then, of course, we have more delays that Chad needs so he can put in editing stuff. Six Bob Ohms asked, how much longer until LUVOIR starts? LUVOIR is, of course, going to be the follow-on telescope to James Webb. It's really going to be the spiritual successor to the Hubble Space Telescope because it's going to be in the optical, it's going to be in the ultraviolet, it's going to be in the infrared, hence the name LUVOIR. And right now, there is no concrete plans to actually launch it. It is the NASA and the various space groups are doing their decadal survey where they give their wish list, and they've asked for 4 different observatories: a high power X-ray observatory, sort of a new infrared observatory that'll be a follow-on to James Webb, and then a planet finding one called HABEX, and then of course LUVOIR. LUVOIR will be an 8 or 15 meter telescope. So just take Hubble, which is a 2.6 meter telescope, and then make it an 8 meter telescope, or make it a 15 meter telescope, maybe bigger. And you can imagine its capabilities will just be astronomical. But right now, there's no plan. LUVOIR will probably launch ideally by 2035. So we're about 15 years away. And that seems like forever, I know. But I remember when James Webb was just an idea. And here we are, just 10 months away from the launch of James Webb. So yeah, who knows what the final form is going to take. And I think, the lessons learned from James Webb cast a long shadow over this entire process. So I don't think that we're not going to see a telescope that is as ambitious in the engineering unknowns that were taken on with James Webb. There was a lot of things that were all taken on simultaneously that led to increased budgets and slipping timelines. And I think anyone who is involved in the project and says, we'd like to build this telescope that's way bigger than James Webb, 3 times bigger than James Webb, people are going to be like, so it'll be $30 billion? So I think we're going to see people be very careful about how they propose this mission. Oh man, these are good questions. I don't know the answers though, so I'll have to hang on to them. Is social media the cause of the Fermi paradox? Maybe. Um, all right. Brian Yuku asks, Solar Cycle 25 just began. Why does the sun even have a cycle and why is it 11 years? So the sun has magnetic poles just like the Earth, just like a magnet. It has a magnetic north and it has a magnetic south. But unlike the Earth, where the magnetic field takes well, hundreds of thousands of years to flip, the sun flips its poles every 11 years. And the whole solar cycle. So in other words, what was magnetic north on the sun 11 years later is now magnetic south on the sun and vice versa. And part of it is the fact that the sun is just a massive incandescent gas. It's just a ball of plasma. And so what you see is during, as it sort of moves, the sun starts with these really pristine, really good sort of lines of magnetic field are on the top and the bottom, and then they sort of expand and get all messy around the poles, and the magnetic fields sort of twist and turn, and then they flip around, and then you get the north and the south, and then it comes back around. And throughout this process, you have when everything's all nice and orderly, you get the sort of the quieter period, the solar minimum, and when everything is very disordered, you get the solar maximum. So when you get the most coronal mass ejections and sunspots and things like that. The question is, why does it happen? And why is it 11 years? And I'm not sure that we fully know the answer. I mean, we know that the sun is rotating at different speeds. The part that we see is rotating from different speeds at different latitudes of the sun. That helps kind of tangle up its magnetic field and makes it weirdly very predictable. And yet, I don't think we really know all of the underlying physics that's going on that causes the poles to flip in the way they do on the timeline that they do, and why some solar cycles are more active than others, why some solar minimums are more minimum than others, and other maximums more maximum than others. Fortunately, there's like 3 brand new tools to help figure this out. There's the Parker Solar Probe, which is going to be flying closer to the sun than anything we've ever seen. We've got the Solar Orbiter spacecraft, which is going to be viewing the sun from above and below, sort of giving us a view of the poles. And then we've got the Daniel K. solar telescope here on Earth, which is the most powerful solar telescope ever built. And those 3 instruments are helping advance our knowledge of the sun. There's still all of these gigantic unsolved, unknown questions about the sun. Like, why is the corona so hot? And what are the underlying physics that cause these various solar cycles? A lot of stuff we just don't know the answers to. And I press answered. Okay. Whoa, good question. All right. Chris Brahm asks, has anyone plugged every science paper and calculation into AI to get the answers to the universe? I mean, you're like half being facetious because, our artificial intelligence at this point just isn't clever enough to be able to figure that out. But at the same time, artificial intelligence is definitely making a gigantic sort of it's helping astronomers make gigantic developments in the field of space and astronomy. So I'll give you some concrete examples. There was a study that just came out just a couple of days ago where astronomers use artificial intelligence to find gravitational lenses. And gravitational lenses are where you've got 2 galaxies perfectly lined up and the foreground galaxy is acting like a lens, like a natural telescope for the galaxy that's behind it and magnifying it. It allows, when you take like a telescope like Hubble can only see out to a few billion years after the Big Bang. But when you get these gravitational lenses, it can see galaxies that were forming just a few 100 million years after the Big Bang. And these gravitational lenses are pretty hard to find. And someone taught artificial intelligence to find them. And it, like, one program found more of these gravitational lenses, and each one is like a boon to science, and it was able to find more than had ever been found by all astronomers combined at this point. There's another recent study where artificial intelligence is now mapping craters, much to the sadness of people working on CosmoQuest. But yeah, so artificial intelligence is now getting really good at mapping craters on other worlds and able to take a planet that's been mapped to the nth degree and be able to find all the craters, big and small. And so I think we're seeing more and more of this. I would love this, like, some way for artificial intelligence to synthesize ideas between different fields. And I wouldn't be surprised if this is already starting to happen, where you've got like some paper over in medicine that's talking about some kind of DNA, RNA, whatever. And then you've got some other paper way over in another field that's talking about something similar, and some artificial intelligence looking at the two papers and going, there's some kind of connection here. Someone should take a look at this. And I wouldn't be surprised if we start to see those kinds of things where disparate groups who are working on roughly the same thing, but they have no idea that another group is working on that, can share their information. And then I guess eventually we'll get to a place where artificial intelligence can start making some interesting new ideas. But I don't think we're there yet. Although we talked about this last week about DALL-E and GPT-3 and just the capabilities of artificial intelligence. Like, it's just getting faster and faster and faster. It's kind of astonishing. All right. Mark Elkin asks, what has a better chance of reaching a star, a generation ship or a seed ship? So just to sort of explain this a bit, a generation ship, like if you're going to send a spacecraft to another star system, you launch a generation ship. People live and die multiple generations on the ship. The first generation goes, and then they have a bunch of kids, and then the kids have kids, and then the kids maybe have like 5, 10, 20 generations. And then that last generation is the one who actually arrives at the star and settles it, which sounds like an awful idea. like welcome to the universe. Your job is to stay alive for 100 years and have children so that they can land on another planet. Like, it seems almost cruel. The idea of a seed ship is that you just send a spacecraft that has like genetic DNA on board, and then when it arrives at its destination, it makes life forms and begins terraforming a planet. That also sounds like a bad idea, because sort of you don't have any, like, you are born and raised by a computer on another planetary system. Like, what's that about? Now, all of this, of course, is the problem with this is that there's this idea of the weight calculation. And we talked about this last week, that if you send a generation ship, like, the only thing worse than going in a generation ship is going in a generation ship and watching the next generation ship fly past you. So in other words, your life is meaningless because 100 years later, they sent a spacecraft that was even faster. And then 100 years after that, they sent a spacecraft that's even faster. And so there's this idea of the weight calculation, and that you need to do the math, figure out the right time to send the spacecraft, and then send it then. Don't send it sooner. Just wait until the right moment, and then there will be a time when it's not possible to send a spacecraft faster. They won't get lapped. And that's when you send the spacecraft. And it's a long time. It's like 700 years. So don't worry. But if I had to choose, I would choose the seed ship. I think putting people on a generation ship is like bordering on a crime against humanity, I think. LDSK asks, do gravitational lenses have forms of distortion analogous to distortions produced by glass mirror-based lenses? They definitely have distortions. When you look at some of the gravitational lenses, and hopefully this is the chance where Chad will show you some really cool gravitational lenses. The one that you want to find, Chad, is called the Molten lens, I think. It's just one of the most beautiful gravitational lenses that's ever been seen. And the incredible part is that astronomers have computer programs that take this lens and are able to essentially reconstruct what the galaxy looks like without the lensing effect. So they can calculate what the distortions from the foreground galaxy are, be able to reconstruct what the original galaxy looked like, and essentially produce a picture and use that to study. And it's absolutely work that they do all the time. And so it's again, like when you think about these gravitational lenses, it's not just the galaxy, but it's actually the halo of dark matter that surrounds the galaxy itself. And so we don't know what dark matter is, but we use it as a telescope, which is kind of amazing. So thanks, nature. Verdadero. Hey Fraser, what will happen first? Will we be able to reach light years distances quickly, or humans will be able to physically be transported to them? Do I get an answer C? None of the above? Will we be able to make a warp drive to fly to another star system, or will we be able to go through a Stargate? So Stargate or warp drive, what comes first? I don't know. I would prefer the Stargate, though. Like, if it was up to me, if I was able to make the laws of the universe and I could only choose one, warp drives or wormholes, I choose wormholes, because I think that being able to just walk to your destination through a big sort of glowy disc is the way. Which, by the way, our plan is to watch Stargate. So now this reminds me. We're watching Succession right now, and then we'll watch Stargate after that. BM Woolgas says, just how prepared are we for the next Carrington event? What kind of damage do you think that it will do to our communications infrastructure? Well, we are not prepared for the next Carrington event at all. When you think about what it would take to be able to be prepared, all right, let me do this again here. So the Carrington event was an event that happened more than 100 years ago, where a really powerful, one of the most powerful solar flares hit the Earth. And it was so powerful that people at mid-latitudes saw auroras. If you're in Jamaica and you see the northern lights, that electricity was jammed down telegraph wires, lighting telegraph poles and equipment on fire. And this was a world that was almost entirely not networked, and there was damage. When you look at today, everything is connected. All of our power lines, all of our electronics, everything is connected together. And so what you're going to get as the flare, as the coronal mass ejection, as this material moves through, it pushes electrons through wires back and forth really quickly in very dangerous ways. And the more that things are connected, the more you can get these breakdowns of routers and power systems, and things will fail and the whole network will go down. And we're not. The solution to the way you deal with a potential big flaring event like this is to have a decentralized power system. So if you've got your own solar panels on your house and you've got your own battery backup, then maybe as the flare goes by, the Carrington event, you're going to have a couple of your electronics in your house break down. Maybe a couple of satellites will break down, but you won't lose the entire eastern seaboard, where all of the transformers melt one after the other and the whole thing has to be rebuilt. So that's the solution. The solution is a smaller grid where it's more decentralized. And in fact, that's the solution that we need for a lot of stuff. We need to have a smaller, more decentralized grid across the board to protect us from the kinds of power events that we already have, brownouts and blackouts. And, here, like where I live, our power went down 3 times this season. So 3 days we were pretty much without power, which is, if I had a battery backup in the house, if I had solar panels, then I would just be laughing about that. But no, I'm completely dependent on a larger grid. So that's the solution, and we are not prepared. But I think that the modern power economy is moving in that direction. We're moving towards decentralization, where your car is a backup battery to your house, and your house has solar panels on it, and you're kind of have your own solar power, but you're also connected to a larger grid, but these pieces can be disconnected over time. So I think we're close to being able to. I would say if the Carrington event happens in the next 20 years, we're going to be in a lot of trouble. But after that, I think we'll be okay. Gaurav Sharma asks, is there any way to predict gamma ray bursts, or do they always come as a surprise? We're still figuring out what gamma ray bursts. So gamma ray bursts, and the amazing story about this is that back in the I'm going to say 60s, 70s, maybe it's 80s, the Americans launched a satellite that was capable of, its job was to watch planet Earth, watch to see any tests that the Soviets were doing, because they would put out this very recognizable burst of radiation. And the satellite started to notice these bursts from across, the universe, not coming from the Earth. And they realized that there was times when you're getting these explosions. And it turns out that these things are called gamma ray bursts. And it used to be that gamma ray bursts were just thought they were just something was causing these things, tremendously powerful. Like one moment, this thing puts out a beam of radiation that is as powerful as the rest of the galaxy combined. But now we know there's a lot of different kinds of gamma ray bursts. There's short period gamma ray bursts and long period gamma ray bursts, and even the different flavors of the short and long period gamma ray bursts seem to be different. And so, in fact, probably in the last maybe week, one of the major discoveries has been that a lot of gamma ray bursts are caused by the formation of magnetars. And so I mentioned this last week again, that there's only about 30 magnetars that have ever been found, and they're a type of neutron star, but clearly something weird is going on that is causing them, where they've got like a binary partner, or they've got some kind of accretion disk that they're forming inside of, they're whipping up this. And it seems now that one of the flavors of gamma ray burst seems to be coming from these magnetars, but another one seems to come from when neutron stars collide, and another one seems to be when some of the largest stars in the universe explode. And each of these events releases an enormous blast of gamma radiation. Can we predict them in advance? Maybe, but not yet. So you can think of some examples. Like if you've got the gamma ray burst is caused by 2 neutron stars that are colliding, you might be able to find 2 neutron stars that are buzzing around each other a couple of weeks maybe before they actually collide, thanks to gravitational waves. You could sort of look for a place that's wobbling in gravitational waves and go, right there, 2 neutron stars are about to collide with each other. And then you wait a week, or you wait 3 days or whatever, and then boom. And so you point at your telescopes, you wait, and then you get the gamma ray burst. With the biggest stars in the universe, you can imagine, again, doing a good survey, finding stars, learning more about how supernovae work, to the point that maybe we can predict when a star like, say, Betelgeuse is going to go off within a short period of time. One possibility is that when you get like a big star like Betelgeuse, when the star is going through the supernova, right, and you imagine the star has been forming all of these heavier elements inside its core, forming this heavy, and it gets to iron, which is the stellar equivalent of ash. You can't get any more energy out of the iron, and so then all of the star starts to collapse in on itself. It's moving down at like 70% the speed of light, and then explodes as a supernova. But the energy isn't able to get out of the star for a while, because it's like the same problem with the sun. The sun is forming gamma radiation at the core of the sun, but this stuff's got to sort of do this random walk to get through the material to get out. But the neutrinos are formed instantaneously as the supernova is coming together, or as the as it's imploding, and they're not blocked by matter. The neutrinos can get out right away, while the radiation has to wait and random walk its way through the wreckage to get out into space. And so there's a supernova warning network that's been developed where people are watching space, looking for this blast of neutrinos from a relatively close supernova, something that goes off within a few hundred, maybe a few thousand light years of us. And that will give us a couple of hours of warning that now the star is about to explode, because the neutrinos are going a little less than the speed of light, but they're able to escape all of that material. And then the radiation from the supernova follows, and you get a chance to actually see the supernova. So I think over time, there's going to be more and more techniques to go, okay, if we see the blast of neutrinos, then we know there's going to be a supernova over there. If we detect the gravitational waves from neutron stars, then we know we're going to see a neutron star collision over there. And over time, we're going to get better and better at predicting the precursor and then the event, which is kind of amazing. That's like science performing, doing the whole circuit, which would be amazing. All right. Nebulous Thoughts asks, hey Fraser, what sources do you get your space news from? You said it before, but I never had a pen to write it down. That's a difficult question. So as you may or may not know, I'm the publisher of the website Universe Today. So Universe Today is the output of all of the work that I do all week. And of course, what I do here on Mondays and the other videos that I do, this is a teeny tiny fraction of my actual job, which is to be the publisher of Universe Today, to be constantly researching in journals and papers and conferences and new press releases and research institutions and following tips and doing interviews with astronomers and astronauts and all that kind of stuff. And so some of the team might even be watching right now today, but we've got about, at this point, probably about 15 writers that work with us in various levels at Universe Today. And my job is to do the story assignments. So every day I sit down for a couple of hours and I browse through all of the sources that I have discovered over 22 years of doing this job. I check all of the universities. I look at all the places where new papers are being published. I check out the news releases from all of the space agencies around the world. I'm looking at, I've got email. People send us press releases and stuff through email. Plus, all the various writers on the team have various ideas for articles, and they also have sources that they're working with. If you want to see kind of like a raw version, the best thing to do is to follow my email newsletter, which I send out on Fridays, because I'm sort of writing up all of the stories that we're producing on Universe Today. But I also provide a gigantic list of links, which is, if you add all of the stories, there's 20, 25 stories that we covered that week, and then you add that big list of links, and sometimes there's about, say, 30 or 40 links. What you've actually got is all of the stories that I considered for that week. The ones that we covered on Universe Today, and then the ones that we just didn't get to. And if you look at those two lists, you've pretty much got my entire list of stories. The other way to do it is if you just watch my Twitter, I'm posting every single one of my of the stories that I'm considering over on my Twitter feed on Cain. And so where I get my stories from is it's like a handcrafted list of places that I check every day, and have been doing this for decades. And so it's not very simple. That's it. All right, I'll go a little longer because I know we're gonna have to cut some stuff out. John Anostis, I've heard you talk about your feelings on the Fermi paradox, but what are your thoughts on non-intelligent alien life out there? I've mentioned the Fermi paradox is such a troubling idea that I think that we're alone in the observable universe, and everybody thinks I'm wrong, which is fine. Bring it on. Come on, aliens. But the question is, what do I think about non-intelligent, dumb aliens? And I actually hold the same feeling, which is that I don't think there's any non-intelligent life out there either, which I know is baffling, but I feel like the evolutionary process to go from non-intelligent life to intelligent life has happened here on Earth. And so if it's happened here on Earth, it will happen somewhere out there. So even if it's incredibly rare, as long as it can happen, then you have the same problem, which is that it happens once in some corner of the Milky Way, and then aliens arise. They make their self-replicating robot probes. They send out their probes to every star system in the Milky Way, and you're back to aliens, and back to like, where are all the aliens? And like, people say, well, like, maybe when you go from single cellular life forms to multicellular life forms, that maybe that's the jump that's really complicated. And I don't entirely buy that. And actually, when I was doing a interview with a biologist, the guy who wrote The Biological Universe, I was talking to him about that, and he kind of agreed with me that you can imagine single cellular life forms producing behavior that is like a more complex life form. We understand the way we work with having, I don't know, mitochondria, DNA, and multicellular organisms, but you can imagine single cellular organisms evolving into some kind of complicated behavior based on their environment, based on just the fact that there's going to be energy coming in and waste and water and all this kind of stuff. And you can imagine like ants. Ants are able to provide more complexity through their complicated collective behavior than one ant. And so I feel like as soon as you get life, then you're on the pathway to making more and more complicated life forms. And eventually you're going to find some place that's going to create intelligence. And then if you get intelligence, then you get self-replicating robot factories across the entire Milky Way, which we don't see. Therefore, you just go back and back and back. And when I sort of run this chain of concepts, we don't see any self-replicating robot factories here, which means there are no intelligent civilizations. And if there are no intelligent civilizations, then there were no unintelligent life forms that evolved into those intelligent civilizations. Anyway, that is the rationale that I follow. But I mean, again, we only have a sample size of one, so we don't know the answer. I mean, the answer should not be that I don't think that there's life in the universe. The answer should be that we should look, we should check, we should do everything we can do to answer this question, because it is probably the most important question that humanity can ask. Are we alone in the universe? Let's build telescopes. Let's build spacecraft. Let's explore the solar system, and let's try to figure out ways to examine the atmospheres and listen for signals from other star systems to get to the bottom of this answer once and for all. That as soon as you assume that there are aliens out there, that there is life out there, then it takes your eyes off the prize. And I think that's that I don't want to get lazy. So let's just assume the worst, hope for the best, and work really hard to see if we can find aliens out there. Apologies, a lot of good questions here. Dico Ravanto. Do you think scooping 3 centimeters of Europa surface sample would be enough to find life on the proposed Europa lander? No, 3 centimeters down on Europa, which is like one of the most irradiated places in the solar system, you're not going to have a good shot at finding life. To really find life on Europa, you're going to need to have some direct sample of water that is underneath the ice and is protected by the radiation on the surface of Europa. And ideally, if you're lucky, there's going to be some geyser on Europa that's blasting out material from a deeper pocket of water, and you can sample that material and find life. But if you're unlucky, then you're going to have to drill down to one of these pockets of water, and they could be tens of kilometers down. So we know for sure that the water is blasting out of Enceladus. So now it's really looking like Enceladus is possibly a better target for searching for life than Europa. But right now, of course, the plan is the Europa Clipper is going to Europa, and that's the plan. So there's no plans right now to send a new spacecraft back to Enceladus, but I'm sure that there will be plans for one in the future. All right, I think I've reached the end. I'm going to give a couple of announcements. So on Friday at 10 a.m., so that's right before Astronomy Cast, I'm going to be interviewing a researcher who's working on a robot made of ice. So we're going to be talking for an hour about how to build a robot, like the ultimate in situ resource utilization. So you take your robot's just a bunch of parts, and then it melts water ice to form claws and grippers and wheels and who knows what else, and repair itself. So we're going to be talking about that on Friday. The week after that, I'm going to be interviewing the writer of a book called The Mission, which is all about the Europa Clipper. So we'll be sort of talking entirely about the Europa Clipper mission. So that'll be in 2 weeks. So we've got lots of good interviews. Again, I'm going to be disappearing this episode as soon as it's over. Thank you to everyone for watching. Thanks to Nancy Graziano for highlighting all of the questions that we tackled today. I really appreciate that. And all the people who did ask questions. Thank you so much. And for those of you, actually, this part will probably not appear anymore. So anyway, so the plan though is if you do have additional questions, go ahead, put them into the comments. Not on this one, though, because it's going to disappear, but on other questions. And I will try to bring them in like I did at the beginning of this show, start the show with some questions brought through from last week. So, all right. Thank you, everybody. And super fun. And I'll see all of you on Friday. Thanks, everyone.